Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So in this session, the first speaker is Thomas Rothvoss, and with the topic constructive discrepancy minimization for convex sets.
Okay, thanks a lot. Yeah, I guess I'm a little bit of an outsider here with respect to the ML community. I hope that there's still some not completely uninteresting stuff for you in the talk. Okay. Good. I want to talk about what's called discrepancy theory, and it's a classical subfield of discrete mathematics or combinatorics. And the setting is as follows: you have some set system over a finite set of points. Actually, not points. Let's call them elements. And what you want to do is you want to find a coloring of the elements with, let's say, red and blue. And what you want to do is you want to find a balanced coloring. So you want, if possible, that for every set you color roughly half of the elements red and roughly half of the elements blue. And the maximum difference between the red and the blue elements in one of the sets, that's called the discrepancy of the coloring. So if you look at this example, then you see that we have a set where we colored both of the elements red. So the discrepancy of this coloring would be 2, and this is the best possible in this little example. And then the discrepancy of the whole set system is actually defined as the discrepancy of the best coloring. There are some nice classical results, like the Theorem of Spencer, which says that if you have an arbitrary set system of n sets over n elements, then there's always a coloring where the difference between the red and the blue elements in any set is at most a constant times root n. And this is great in the sense that if you just take a random coloring, then the random coloring would be a root log n factor worse. So one actually has to do quite a lot of work to get this bound. Another nice result that kind of is a little bit surprising is the theorem of Meka and Fiala that's even a little older, and it says that if you have the special property that every element is in at most t of the sets, then you can even bound the discrepancy only linearly in that so-called frequency t. So if you look at the method that is used in particular in Spencer's theorem, then this is the somewhat standard technique. It's called the partial coloring method. And the idea is that we are relaxing our goal a little bit, and instead of finding a coloring for all of the elements, we are happy if we can color a constant fraction of the elements. Let's say half of the elements. And mathematically, we would say that we're kind of allowing to use the color 0 for, let's say, half of the elements. And it turns out that this actually makes the whole thing a little bit easier. So this gives us more flexibility. If you look into the proof of Spencer, then what he actually does is the following. He doesn't immediately show that there exists a full coloring for your elements with root and discrepancy. He shows that there exists such a partial coloring. So he can color, let's say, half of the elements with the root and discrepancy. And then what you do is that you take the half of the elements that you colored, you throw them away, so you forget about them, and then you repeat with the remaining half. And the trick is that now you have a smaller instance. So the discrepancy guarantee that you get for the partial coloring in the second iteration is a little bit better than the one that you had in the first iteration. And if you continue this game, then you can actually see that the discrepancy that you get over the iterations, it gets smaller and smaller and smaller, and you get a nicely convergent sum. So overall, you're only paying a constant times that original root and discrepancy to color all of the elements. Good. Let's have another look into the proof of Spencer's theorem, and let's see what he's actually doing. And let's take a more convex geometry perspective. you can imagine that this is the hypercube in n dimensions, and each of the vertices of the hypercube shows you one of the potential colorings that you could choose to use. For example, the point in the right upper corner, 1, 1, that corresponds to the coloring where you would color, let's say, both of your two elements with blue. Okay. Now, how in this geometric setting, how does the set of good colorings look like? Well, if you have n sets and n elements, then you can actually write down some linear constraints. And what you actually would want to write down is that for every set, if you sum over the elements, then you're getting a value that's between minus some constant times root n and plus some constant times root n. So actually, the set of good colorings, in a fractional sense, it's defined by the intersection of n, let's call them strips. Right? So for every set, we get one strip. So the whole set of good colorings is the intersection of n of those strips. Okay, but how does this perspective actually help us to find a coloring? Well, you could now. Okay, so let's make some observations. So first of all, what we really would like to do is we really would like to find one of the vertices from the hypercube in that set K, because we know that the vertex corresponds to coloring and the set K corresponds to the points of good colorings. Or if we relax the whole setting and we're happy with the partial coloring, then we would be happy with a point that doesn't need to be a vertex, but it should lie in some lower dimensional face of the hypercube. So it should be a point that has a lot of coordinates, either +1 or -1. Okay. Now, let's do a little bit of math, and let's try to use the fact that this set K is the intersection of strips. And each of the strips has a width of, let's say, 100 to each direction. What this actually means is the following. It has the implication that if you count what is the Gaussian measure of this set K. So Gaussian measure is the following. You take a random Gaussian with a standard deviation with variance 1 in every direction. So you take the standard Gaussian and you check what's the probability that the standard Gaussian ends up in K. That's the Gaussian measure gamma n of K. And this Gaussian measure, it's lower bounded by the product of the Gaussian measure of all my n strips. I'll explain a little later why this is the case. But if you have a strip, it's easy to calculate what's the Gaussian measure. It should be some constant that's very close to 1. So you get some lower bound that is exponentially small, but it is mildly exponentially small. And here's the trick, that any convex symmetric set that has a Gaussian measure that is that large will definitely have a point in it that has a lot of ±1 coordinates. I will not show you that argument. Essentially, the argument would be that you take those 2 to the n many hypercube vertices and you put translates of K. You place translates of K at each of those hypercube vertices, and then you argue that, well, you must have a lot of overlap going on. And then you take some of the overlapping sets, and then you take the difference vectors. That will actually give you those partial colorings. What I want to give you is actually an algorithm to do the same, more or less. Okay, good. I have actually implicitly used on the last slide a nice lemma by Shidak and Khatri, which goes as follows. Suppose you have two sets, K and S, and what you know is what's the Gaussian measure of both of them, and what you want to estimate is what is the Gaussian measure of the intersection of K and S. And the good news is there's an easy lower bound. You just take the product of K, the Gaussian measure of K and S, and that gives you a lower bound for the Gaussian measure of the intersection. The assumptions that we're having here is that one set K is convex and symmetric, and the other set should actually be a strip. This is conjectured to work for any convex symmetric sets, but it's only proven if one of the sets is actually a strip. Okay, good. In other words, this is a very nice tool to get a lower bound on the intersection of strips with convex sets. Okay. Good. So let's compare a little bit what is known on partial coloring approaches. There was the theorem of Spencer with some kind of extensions by Gluskin and Giannopoulos, and all those approaches, they're all based on a counting argument, where essentially you use the pigeonhole principle with exponentially many pigeons and pigeonholes. And the problem is that this does not give you an algorithm. But we would really like to have an algorithm. But already for the original setting of Spencer's theorem, it took about 25 years until somebody, Nikhil Bansal, came up with an algorithm that was a little bit complicated. It was based on iteratively solving a semi-definite program. And actually, it was very custom tailored to Spencer's setting. But fortunately, 2 years later, there was a more general algorithm by Lovett and Meka, which works, which is a very elegant, simple Brownian notion, and it works in a much more general setting. So it actually works whenever you have a polytope, whenever K is a polytope, which satisfies the property that it's large enough. So if you look at this this quantity, then here. Then it's maybe hard to digest what this means. But if you plug in this condition into the lemma of Schiedak and Khatri, then what you get is that the Gaussian measure of this polytope K is so large that also the counting method would actually give you the existence of a partial coloring. So whenever you have such a polytope, you can actually have an algorithm to find those partial colorings. However, the disadvantage is that maybe you have some convex set K, the measure is large enough, but you couldn't use just that simple lower bound of Schiedak and Khatri to infer that. And this is the main theorem, the main result that I'm going to show here. It's that actually you can get the most general case. So this is the main result that I want to show here. And it goes as follows. You take any convex symmetric set K, so like this set K, and it's possible to find a vector y like this one, which is in the intersection of K and my n-dimensional hypercube. And the property of the vector y is that a linear number of coordinates will be either plus or minus 1. And the condition that I need for my set K is that the Gaussian measure is at least mildly exponentially large. Okay. So this is essentially the existence theorem, and now there's an algorithm for it. We can do all this stuff in polynomial time. And here's the whole algorithm. Step one is you take a random Gaussian, let's call it X star. Okay, if you take a random Gaussian, then it's extremely unlikely that this random Gaussian will be in K or will be in the hypercube. So this point is definitely not going to do the job. But here's the trick. You compute the point y star that lies in the intersection of K and the hypercube, and you take that point y star that is closest to X star in terms of the Euclidean distance. Okay. So by definition, y star is in K intersected the hypercube, but the claim of the theorem is that actually this point y star has the property with very high probability that a linear number of entries will be either plus or minus 1. Okay, so good. So essentially, Alon and Spencer in their famous book, they actually conjectured for a very long time that this whole partial coloring approach would be impossible to make it algorithmic. So it is actually surprising that such a simple algorithm actually can give you this partial coloring. Okay. So from a more abstract perspective, what you would say is that you're kind of looking at a random extreme point of X intersected with a hypercube, and a random extreme point is actually going to have the property that we need. Okay. And not only is the algorithm simple, also the proof is actually simple. So I hope that I can go through the whole proof. Okay. Is there any questions so far? Okay, good, thanks. Okay, there's one hammer that we need for the proof, and that's the so-called isoperimetric inequality for the Gaussian space. And the idea is as follows. You have any set K, and we want to consider another set K delta, which is all the points in K plus those that are at distance at most delta to K. So in other words, we take a set K and we make it a little larger. So we throw in any point of distance at most delta. And we're wondering how does actually the Gaussian measure grow with delta? And here's the claim. The claim is the following. Even if you have a set K where the Gaussian measure is exponentially small, you need to add only points of distance, a small constant times root n, and then the set will cover almost all of the Gaussian measure. So this is essentially the fact that Gaussian measure most of the Gaussian measure is not further away than a small constant times root n from each other. And where's the isoperimetric inequality? Well, the Gaussian isoperimetric inequality actually tells you that if you want to show such a claim, then the worst case are precisely half spaces. So it actually suffices to look at the one-dimensional case. So you can imagine that you have a one-dimensional interval that goes from -infinity to some point, and that has a Gaussian measure exponentially small. And you now just need to estimate by how much do you need to shift the boundary of that interval until the Gaussian measure is almost everything. And then you do a one-line calculation, and then you come up that, well, actually, you need to shift the boundary only by essentially the root of that exponent that you had. Okay, good. So far we learned the one thing that we need, which is that Gaussian measure is not far from each other. Okay, and yeah, now we have actually everything for the analysis, which fits on one slide. And here's how the proof goes. Okay, so what did we do? We did take a random Gaussian x star, and then we calculated what is the closest point y star that lies in K intersected the hypercube. So first of all, what do we know about 2 minutes? Okay. Okay, so I have to speed up a little bit. Okay. Okay, so we do know a couple of things. We know that the distance has to be at least a fixed constant times root n. Already because the distance of a random Gaussian to the hypercube is that large. Okay, on the other hand, we learned that that x star would be close to any set that's large enough in terms of Gaussian measure. Okay, so the only thing we need to do is to find in this picture a set that's large enough in terms of Gaussian measure. And here's the trick, that actually what we are solving is a convex optimization problem. And now for a convex optimization problem, you can take constraints that are not tight, and you can throw them away. And that's not changing the value of your convex optimization problem. And that's what we're doing. So you look at your point y star, you throw away the hypercube constraints that were not tied, you get a bigger set. And now you can estimate that this bigger set must have a large enough Gaussian measure. As it has a large enough Gaussian measure, from the isoperimetric inequality, we know that a random Gaussian point would be close to it. And that's a contradiction, because it would be closer than this 1/5 times root n. Okay? Good. So these are essentially all the arguments. We would probably need 2 or 3 minutes more to digest this properly, but that's it essentially. Okay, good. Okay. Then let me close with some remarks that actually this whole discrepancy theory, it's not just an obscure area of discrete math. It's actually very useful, and the best approximation algorithms, for example, for bin packing, they actually use those type of arguments. Okay, so let me close with my favorite open problem, which is the following, that if you are in this so-called Beck-Fiala setting, so you have a set family where every element is in at most t sets, can you get me any better bound than just 2t on the discrepancy? Thank you.
Any question?
So is Beck-Fiala constructive?
Yes.
Immediately from...
Yeah, immediately from the proof. It's essentially you're solving a linear program, you're throwing away constraints, then you resolve the linear program, and so on.
John?
I don't quite see why your algorithm is polytope in general, because couldn't there be an exponential number of faces on your polytope, and then finding that projection will be exponential?
Oh, the number of faces is exponential, but you're essentially only solving a convex optimization problem. So K is convex, the hypercube is convex, so you're only trying to find the closest point to some convex set. And that's essentially a convex optimization problem.
But still, it's an assumption that you can do this in polytope. It's not true for any convex set.
Okay. You need to be able to solve the separation problem for K. Okay, sure.
Yeah, which is not always possible, right? In polytope.
Okay. That's an assumption.
Okay.
Well, if you don't know K, then okay, what are you doing?
Any other questions?
So the isoperimetric property, in terms of the growth of K, you have a bound on the probability, upper bound of 1 minus the thing. Why is it not? It seems to be the case that it was just the ball was D-dependent, but the actual bound was no longer D-dependent. Maybe if you go back to that slide.
So there's no dependence on the dimension.
No, not the dimension D. This the metric D of xk. So why is it the case that in this lemma, the right-hand side, the implication is not dependent on D? The way in which you're measuring, or is this, or you just maybe I missed it. Is this Euclidean? D.
Okay, actually, this is okay. It would actually be independent from the dimension. This is minus some exponent. This is essentially 3 times the root of the exponent, and this is again minus that same exponent.
I'm not talking about the dimension, the ambient dimension. I'm talking more about D of x comma k. The distance.
The distance.
Yes. Why is it not?
Oh, sorry. The big delta. You would choose it as being. This 3 root delta n, that would be your big delta in this case.
The metric has to be a Euclidean metric?
Euclidean.
So the assumption is it's Euclidean.
Yes,
okay. All right.
yes.
That answers the question.
So let's thank the speaker again. So our next speaker is Sebastian Lovett from MSR, and the title of his talk is Optimal Discovery with Probabilistic Expert Advice.
Thanks. Okay, so I'm going to tell you about a problem I worked on 2 years ago. I will try to describe to you an algorithm that does something. The problem is that I don't know exactly what are the good applications for this algorithm, but I think there are actually many, and I will suggest 2 of them, but I think there are more. So essentially, the problem I'm looking at is the following. I'm searching for something, and I have a few heuristics to do this search, and I want to combine those heuristics. So imagine, for instance, that I'm trying to debug some code, okay? And I have several heuristics to find inputs that will likely make my code fail. And what I want is to combine these heuristics in a smart way. That will be one of the two applications that I thought about. So here is the problem slightly more formally. So we have X, which is a countable set. So think of X as the potential input to your algorithm. And we have a subset A of interesting items. Okay, so what are these interesting items? These are the inputs that will make your algorithm fail, that will make your algorithm bug. Now what you have is that you have access to X, to the input that you can give to the algorithm through experts. These experts, so these are the heuristics that you have, and they correspond to probability distribution over your set X. Okay, so using your heuristic, you can generate at random inputs to your algorithm. And the goal is to find as rapidly as possible many elements of A. Okay, so you just want to use this heuristic in a certain way to rapidly find all the inputs that will make your algorithm bug, and then debug it. Okay, so let's again do it one more time, slightly more formally. So we have K experts. Okay, this is known to us. These are the K heuristics. What is unknown to us is a set. Let's say what is unknown is a set of potential input X. The set of interesting items is of course unknown, and the distributions corresponding to the experts are also unknown. And what we do is that we play a sequential games that goes as follows. So as t goes on, at each time step, what I'm going to do is that I'm going to select one of those k heuristics. Okay, so I select one of those k experts. So let's say I select I sub t at time t. And then what the expert or the heuristic does is that it generates at random an item. So we will use the terminology item, but you can think in terms of input. So it will generate an item yt in X at random from the underlying probability distribution, which is new it. Okay? And this drawing is independent of everything else. Now what we have this input, so if you think in terms of the application to debugging an algorithm, then you test this input and you see if the algorithm works or it doesn't work. Okay, so you learn whether yt is in A or not, whether yt is an interesting item. And what is your goal? Your goal is to, again, find rapidly as many elements of A as possible. So what you do is you have observed y1 up to yn. These are the inputs that you have tried, and you look at the intersection of this with A. So that's the number of, and you look at the cardinality of this. So that's the number of interesting items that you have found. Okay, so of course, if you find 2 times the same interesting items, it was only interesting the first time. Okay, you don't care about finding it twice. Okay, so is the problem statement clear? So what I'm going to give to you in this talk is an algorithm that solves this problem and that does really well in practice, and which is super fast and could be useful potentially. So let me give you maybe another potential application for this framework, just to give you an idea of where I think it could be used. And this was actually the original motivation. This is a problem of security analysis in power system. So imagine you have the grid, okay, you have a power system, so this is a big network with many nodes, and what you want to do is you want to find the faulty nodes in your network. Okay, and what you can do is you can actually go check, if you want to check if the node is faulty, you have to actually go there, check it, and then you can fix it maybe potentially. Okay, so this network is huge and you cannot go check every single node. But what you have is that you have a bunch of, so you have this network and you have faulty nodes in it, so these are the important nodes. So you cannot go check every node, but you have a bunch of engineers working for you, and they are smart, and they came up with different heuristics to explore this network. So engineer 1 is heuristic is, let's say, supported on this subset of the network. Engineer 2 prefers that one, 3, etc., 4. So you have these different heuristics, and what you can do is that if you go to engineer 1 and you ask him, okay, what should be the next node that we check, he will do something which we model as he draws at random a realization from its underlying distribution, and he will give you a node, and then you can go check and fix it if it's a faulty node. Okay, so that's another potential application, which is actually a real application. I didn't follow up with the guys with whom I did that, but I think they actually used it. Okay, so let's try to think about how to solve the problem. It will be also reasonably interesting mathematically. So here is what we want to do. Imagine that we knew the probability distribution nu1 up to nu k. What would we do? Here is a very simple strategy which sounds like a pretty good idea. So we have already observed y1 up to yt. These are the items that we tried. So now, let's say we know everything, okay? So we also know the set of interesting items. So the set of interesting items that is left to be discovered is A minus the set y1 up to yt. And now for each expert, I can look at what is the probability that this expert will give me an interesting item that I have not seen yet. Okay, so this is this nu I, okay, the probability of the set A minus the set y1 up to yt. That's the probability that expert I will give me an interesting item that I have not seen yet. And what I can do is that I can, it's smart to just query the expert which maximizes the probability of giving me an item which is interesting and that I have not seen yet. That seems reasonable. Of course, it's not an algorithm. I cannot do that, but if I could do that, so first of all, let me tell you that this quantity nu I of A set minus y1 up to yt, this is known as the missing mass of interesting items for expert I. So what we prove, okay, I call it a theorem, but it's more like a proposition. It's something fairly simple. Under the assumption that the experts have non-intersecting supports, meaning that if I look at the support on the interesting items, they are non-intersecting. Okay, so this is a very strong assumption which is not realized in practice, but the two theorems that I will tell you hold only under this assumption. Okay, but I will show you experiments where you will see that it works even without it. But okay, if we have this assumption, then this strategy, this greedy strategy, is actually optimal. So precisely, this strategy of selecting at each time step the expert that would maximize the probability of giving me a new interesting item that I have not seen yet, this strategy maximizes at any point the expected number of interesting items that I have found so far. Okay, so this is the optimal strategy. If the assumption is violated, then this is not true. It's a much more complicated problem, and a greedy strategy will not solve it. Okay, you have a big MDP basically to solve, and it's most likely intractable. Okay, good. But now, more interestingly, what we want is a data-driven strategy. Okay, so we want something that doesn't require to know the probability distribution nu1 up to nu k, and that doesn't need to know the set A, etc. So what we need is to find an estimator for this MIT, the missing mass. And this is called the Good-Turing estimator. Okay, this is something very well known. So you know, Turing during the Second World War, he was at Bletchley Park and he was trying to crack the Enigma code. And one question that he was asking with his intern Good is the following. Look, we have seen that many code words for the Enigma machine. How many code words have we not seen yet? Okay, so the question is, given what we have seen so far, how can we estimate what we have not seen yet? And this is a good Turing problem, and Good and Turing came up with an estimator which is really beautiful and really simple. And if you think about, that's what anyone would come up with if you think about this problem. So here it is formally. So let's say that we have a sequence x1 up to xn, IID from some probability distribution nu supported on x. I'm interested in the random variable m sub n, which is the missing mass on A, so it's the probability that is left on A once I remove the points x1 up to xn. Okay, this is the missing mass on A. This is a random variable, and I want to estimate it. And here is the estimator, the Good-Turing estimator, mn hat. So what I look is the following. So let's look at this indicator for any point x in A. What I look at is whether x appears exactly once in my data set. If it appears exactly once, then I count it. If it appears twice or if it doesn't appear, then I don't count it. Okay? And I look at the frequency. Okay, I divide by this 1/n. I look at the frequency of items that appears exactly once in my data set. And this is called the Good-Turing estimator. Okay, it's as simple as that. So this thing, an element that appears exactly once in my sequence is called an apex in linguistic. And here is a theorem. Okay, so I should cite also Good and Turing, 53. But this is a theorem that will tell you the properties that we need for the algorithm, concentration properties of this estimator. So the first thing is that this is a good estimator. So this was proved by Good and Turing in the sense that it's unbiased. meaning that if I look at the expectation of mn minus mn hat, okay, both are random variables, but if I look at the expectation of the difference, then this is small. It's smaller than 1 over n. Okay, so this is quite deep. I mean, it's not at all obvious that you can have that. It's rather simple to prove. It's essentially 4 lines. I mean, it's 4 good lines, but it's only 4 lines. And then, okay, McAllister and Shapir, and then McAllister and Ortiz, they proved the following concentration bound. So with probability at least 1 minus delta, you can actually show that mn is sandwiched between mn hat plus minus something that looks like square root log 1 over delta over n. So if you know about Hoeffding's bound, I mean, this is exactly what you get in Hoeffding. But the situation is much more complicated. Okay, we are not summing just IID things. So let's think just for a minute how you would prove that. It's actually very, very simple. So we know by the first thing that I said that in expectation, the difference is small. Now I'm going to tell you that mn concentrates around its expectation and mn hat also concentrates. Okay, so that will imply this thing. So why mn hat concentrates around its expectation? It's just Mach-Diarmid inequality. Look at mn hat. If I change one of the value in my data, one of the xt, it doesn't change much for mn hat. Okay, so there is this stability property which implies concentration immediately. So immediately we know that this the last equation is true if I replace mn by the expectation of mn hat. Okay, now what about mn? Mn is much more complicated. So if I had a board, I would write, what would I write? I would write that m is the sum over all the element x in A of what? Of the nu of A, of nu of x, okay, the probability of x, times the indicator that x is not in my data. So this indicator that x is not in my data, this is a Bernoulli distribution, but now these different Bernoullis are dependent. Okay? So I cannot just apply Hoeffding inequality. But the trick is that they are negatively correlated. So if I know that one is 1, then the other ones are more likely to be 0. Okay? And we know that Hoeffding's inequality, and more importantly in this case, Bernstein inequality, generalizes immediately to negative correlation. Okay, so again, it's just 2 lines, and you get this theorem, which if you think about it, if you were trying to, if we didn't know about Mach-Diarmid and Bernstein and all this stuff, it's amazing that you have such a concentration property. It's really non-trivial. Okay, good, but we have that. So now what I'm going to do is going to be very simple. I have this estimator for my missing mass for each expert. So what I could do is instead of picking the one which maximizes the probability, I pick the one which maximizes the estimated probability. This would be terrible, okay? Because if I do that, then I mean I could estimate, just the first time I pick expert 1, I pick it 2 times, and it just by lack of luck, I just got 2 times the same interesting item. So now I believe that the missing mass is 0. Okay, so it will take me a very, very long time to come back to this expert. Or actually, I will never come back to this expert. Because now I have estimated the missing mass to be 0. So I need to be careful and boost it by some confidence. Okay, so for those of you who know about bandits, this is an idea that has been around since '85, since Lai and Robbins. You don't just trust your estimate, you boost it by a confidence bound. So that's what we are going to do. Now we have a confidence interval given by this theorem. So we designed this algorithm which we call Good-UCB. UCB stands for upper confidence bound. So we replace the unknown missing mass MIT by its estimator, and we boost it by a confidence interval. So now the algorithm is to sample, to follow the expert that maximizes the estimator, the Good-Turing estimator for the missing mass of expert I plus this confidence term. Okay, and where TIT here is the number of times that I tried expert I. Now I just want to give you one actual theorem, something non-trivial, so let's do it. So how do we assess the performance of Good-UCB? So one thing that we could do is to look at how many items it found at some time t, and we want to compare this to how many items found by the optimal strategy. Okay, so that's what we want to do. Note that what we want to show is that this difference goes to 0, because eventually any strategy will find all the interesting items. So it's not like in a standard bandit setting where you're fine with a regret that grows like square root t. Here we want something, a regret, a cumulative regret that actually goes to 0. Okay, so this is much more tricky, and the reason is that there is a sort of restoring property, meaning that if you have an algorithm that takes a bad decision at a given time step, then it will have more good options later on. So if I do badly now, then in the future I can do better because I didn't find the items before. And I need to exploit this property in the analysis, so that makes things a little bit trickier. So let me just tell you the theorem. So I define T of lambda to be this. It's the first time T at which the missing mass of all the experts is smaller than lambda. And T star of lambda is the same time, but for the optimal strategy. And now we prove what we call a nonlinear regret bound. So we show that again under this assumption of non-intersecting support. So let S be larger than 1. Think of S, let's say, as 10, something like that. Then with high probability, with probability something like 0.99, for any lambda, okay, this is the key. It's uniform in lambda. So uniformly at all scales, the time Good-UCB needs to lower all the missing mass to lambda is of the same order as the time it takes for the optimal strategy to lower everything to lambda minus a little bit. Okay, so when I have put everybody down to lambda, I'm lagging a little bit behind the optimal guy who put everybody down to lambda minus 0.1, something like that. Okay, so this theorem is just telling you that you lag a little bit behind the optimal strategy. So let's jump into the experiment and you will see that it's actually doing something. So this is so 4 experiments. It's the following setting. So the total number of items, the total number of inputs is in the first one 128, in the second one 500, third one 1000, fourth one 10,000. Okay, so I augment the size of the input space. Now I have 7 experts, 7 heuristics. Every item is interesting. The first expert has a probability, the first time you try it, of 51% to give me an interesting item. Okay, so basically if I have 100 items, 51 of them, the expert 1 puts mass on 51 of them. You see expert 2, 25, etc. Now I tried 3 different strategies. One of them is just a round robin. Okay, so I have 7 heuristics, so I try heuristic 1, then heuristic 2, etc. Okay, so I just round robin through them. One of them is the oracle strategy, the absolute optimal strategy, which we can compute in this case. And the third one is Good-UCB, our algorithm. So the top one, what I'm plotting is, as a function of time, the number of interesting items found. Okay, so the higher the better. The top one is, of course, the oracle, okay, the optimal strategy. The second one is our algorithm Good-UCB, and the third one is uniform sampling. And you see, as I augment the size of the space, actually Good-UCB becomes as good as the oracle. Like, it's not even lagging, it's doing as well as if I knew everything, but it knows nothing. So yeah, it's doing well. So we call this property, you see, there is some kind of limit. We call this the macroscopic limit, and okay, if I had more time I would tell you what it means exactly, but it's a simple corollary of the nonlinear regret bounds that I just showed you before. And now to conclude, I want to show to you a completely artificial example where the supports are intersecting, and having a series that explains this would be very interesting, but we don't have it. So here we have how many? We have 5 experts. So the set of points are the set of positive integers. That's the set of points, and the set of interesting points are the prime numbers. And each heuristic is just a geometric distribution on the integers. Okay, with different mean. Okay, the first one has mean 100, second one 300, etc. And we run Good-UCB, and again we compare, and we run with different value of this constant C. And if we take C a little bit smaller, it's more aggressive. So as always in practice, the more aggressive you are, the better things go. And you see that it's doing actually really well. Like it's lagging a little bit behind the oracle, but it's doing almost as well. So these are the references. So the paper appeared in 2013. And you can also check the surveys that I wrote on Bandit, which give you some intuition about where these ideas come from. Thank you.
questions?
For the last experiment,
Yes.
how did you compute the oracle strategy?
Okay, excellent question. So this is the oracle greedy strategy. It's not the true oracle. I mean, it's what I call the oracle in the talk, but it's not the true optimum. I think you could probably do it in this example, but we didn't. It would be actually quite interesting to see how big is the gap. That I don't know. Good question.
Any other?
Have you thought about what kind of pathological cases might look like in the case of overlapping experts?
Yes. So things can go really bad, and I mean the simplest example that we found is you need, like with three experts, I could not find an example where the two would be different, where the greedy would be non-optimal. So we needed to go to 4 experts, and then if you go to a large number, then you can show that really as the number of experts grows, the gap between greedy and non-greedy can also grow. It's unbounded.
Actually, I have a similar question.
Yes.
I mean, the problem, at least the initial problem, seemed very reminiscent of set cover, and the
yes.
and the non-intersecting
That's right.
expert seems like set cover where the sets don't intersect, which you can solve exactly.
That's absolutely true.
And have you looked at? I mean, there are many approximations, and set cover is approximable.
Yes.
Which would then relax the requirement to have non-intersecting experts. And I was wondering if that could sort of compose with the other approximations, because in some sense it's sort of a stochastic non-intersecting set cover, which you
absolutely. So I did not, but I'm really hoping someone will do. This, yeah. I think this is exactly the way to go.
Yeah.
Okay. All right, let's thank the speaker again.
Hi, everybody. So today I'll be talking on a class of distributions defined via submodular functions, which we shall call the submodular point processes. And this is joint work with Jeff Bilms. So basically, we introduce a new class of distributions which we call submodular point processes, or SPPs. And these are distributions directly proportional to a submodular function. And another class of distributions which we shall kind of relate to a lot is the class of log submodular distributions, which we call Log-SPPS, and they are basically proportional to the exp, or the exponent of a submodular function. And in this talk, I shall try to kind of compare theoretical properties and results of both of these distributions. So some motivations for both these classes of distributions. Essentially, submodular functions have very naturally been used for a number of applications, a number of real-world applications in the context where one would want to define these distributions with a submodular function. They are natural in applications where one wants to do something like diversity and coverage. So sensor placement, summarization, or diversified search are natural applications where one would want to use these distributions with a submodular function. You can also define these distributions with a supermodular function, and kind of natural applications of these would be where one wants to kind of model notions of attraction or cooperation, and applications are like image segmentation, clustering, etc. So a question is that since submodular functions have very naturally been used in many of these applications, and in many cases, certain times these models have been probabilistic, a kind of natural question then is, can we define a general class of probabilistic distributions which can be defined via general submodular functions? And how hard is probabilistic inference with these kind of distributions, and what kind of guarantees can you give for probabilistic inference? So it's well known that submodular functions can very easily do things like map inference, but probabilistic inference was kind of an open question. So the first result is we show that that for general classes of submodular functions, it's really hard to compute these. So basically, it's kind of, this is in fact independent of p is equal to np. So you can kind of give information theoretic proofs that computing the normalization functions for both SPPs and log-SPPs is hard. And one can kind of give lower bounds of order log n and order n, respectively. On the other hand, we can also show approximation guarantees that for SPPs, you can actually compute an approximation which is order log n. And it was shown in the context of log-SPPs by Jalonga and Kroza that you can actually get an order n approximation. And the idea is to use sub and super gradients of a submodular function. So basically, though these properties are known, a number of subclasses of submodular functions actually admit exact probabilistic inference for both SPPs and log-SPPs. And a kind of interesting open question is, what are the other such distributions that can be characterized that admit efficient distributions? And finally, I would like to kind of complement the two. So SPPs and log-SPPs both model diversity cooperation, map inference is efficient, and probabilistic inference can be done either approximately or exactly in some special cases. But the complementarities are that SPPs have kind of low dynamic range, whereas log-SPPs due to the EXP have a high dynamic range. So it's very interesting that SPPs actually are kind of closed under sums, so they are very natural in modeling mixtures, whereas log-SPPs are closed under products, so they are useful as priors. So an application of this kind of theory would be to give alternate directions in learning mixtures or other compositions of submodular functions. So thanks a lot, and if you have any questions, you can come to my poster.
So we are done with the first half of the event today, and let's thank all the speakers that did a great job here today. And we're going to start the poster session now. The poster session is going to be in the McKinley room, which is just the other side of the building. And we're also going to open the polls now. So we have awards for the best poster. So make sure to vote for your best poster. Note that we had more than 20 posters. So not all of them had a chance to present their work as a spotlight. So make sure to check the other posters as well. They are as good as the one that were presented over here. So thank you, and see you at the McKinley room with a reception and some food, free food again.